Welcome, class. This is the Chapter 6 Study Team Test Solutions. In addition, I've added 8 extra slides at the back of this deck that involve questions from the individual test. Please spend your time wisely using this to review. This is long and it's not intended for you to watch everything, but definitely go to the questions that you missed. I suggest pausing the video, trying to do the problems, watch the solution, and then start with a fresh piece of paper and try again. Practicing solution, practicing those little skills about paying attention to details, what you're multiplying by, what you're dividing by, what are your variables. As you practice that, you're going to eliminate a lot of the simple errors that brought down many of your scores. So good luck, and I hope you use this well. Consider the sequence that goes 3 to 7 to 11. Write the next 4 terms in this sequence. As I look at the sequence, I can see as I move from 3 to 7, I am adding 4. And as I move from 7 to 11, 7, 8, 9, 10, 11, I'm also adding 4. So I understand that every single time I'm adding 4 to get to the next term. So it says the next 4 terms. So I've got 11. So the next one would be 11 plus 4, which is 15. And then if I add 4 to that, I'm at 19. And if I add 4 again, I'm at the number 23. And then finally, if I add 4 one last time, I'm at the number 27. So those would be the next 4 terms in the sequence. The generator for this sequence is each time I'm adding a value of 4. I'm adding 4 each time, positive 4. What kind of sequence is this? How can you tell? This is an arithmetic sequence. And I can tell it's arithmetic because I have a common difference. Right? Every single time the next term is 4 more than the previous term. So my common difference there is a value of 4. And then finally, write the explicit formula. Well, for an arithmetic sequence, right, the value of the nth term is equal to your generator, right, times the variable n, and then plus your 0th term. So this value right here is your generator, and our generator is positive 4. And this is the 0 term. It's actually not part of the sequence itself, but if I back my sequence up and back it up in time, I could get the 0 term. So for example, my sequence starts with a 3 followed by a 7 followed by an 11. And I know to move forward, each time I'm adding 4. Move forward, I'm adding 4. Well, this is the first term, the second term, the third term. If I want the 0th term, instead of adding 4, I could subtract 4 just once. And 3 minus 4 is, that's negative 1. So I believe my, and then if I move forward from that, if I have the number negative 1, for example, and I add 4 to that, I should land at the number 3. So my 0 term is negative 1. That means that the explicit formula, right, any particular value I wanted, right, the nth value would be given by the formula 4 times n and then minus the number 1 because my 0 term is a negative 1. Let's see, so question 2 from the first page says simplify by writing with all positive exponents. So when we're finished, we have to make sure all of our exponents are positive. So in A, I'm actually multiplying 1, 2, 3, 4, 5 different things. I've got an x to the negative second, a y to the fourth, times a 4 times an x to the fourth times a y to the negative ninth. So I'm going to reorder these things using the commutative property. So I'm going to bring this 4 all the way up to the front, and I'm going to multiply it by an x to the negative second, and I'm going to multiply that by x to the positive fourth, and then we're going to multiply that by y to the fourth, and then we're going to multiply that by y to the negative ninth. Definitely not a requirement to put these things like that, but I like this because I can see exactly what I'm combining, and it makes it a little bit clearer in my mind what's happening. By the way, if you have a constant like the number 4, and that 4 is not being raised to a power, it's 4 and x is getting raised to the fourth, I like to put those in the front. By convention, we do that. So when I combine x to the negative second and x to the fourth, I can't get that by addition, right? Negative 2 plus 4 is a positive 2. It might help to think about this. If I took x to the fourth, we know by definition x to the negative second, those two factors of x belong in a denominator, right? And if I look at this, this is 4 factors of x over 2 factors of x. There's a giant 1 right there, and what I'm left with is x squared. So again, when I combine 4x to the negative second and x to the fourth, I get 4x squared. Because this giant 1 this is just the number 1, and 1 over 1 equals 1. So I'm left with x squared. Let's do the same thing with the y's. I've got y to the fourth, and in my denominator I have a y to the ninth. So I'm going to move those 9 factors of y into the denominator. It's going to be y to the positive ninth. Now, if I simplify that, that's y, and down in my denominator I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. That's crazy that I wrote those all out. But you can see I do have a giant 1 here. Here's 4 factors of y, and 1, 2, 3, 4 factors of y. So that doesn't look like a giant 1, but it is a giant 1 because I've got 4y factors over 4y factors. So that just equals 1. And I'm left here, if you look, there are exactly 5 factors of y in my denominator. So it says make sure you write with positive exponents. So I'm gonna write this like this. This is the same as 1 over y to the 5th power. And you can see that, the shortcut, if I was to combine those via addition, right, 4 plus negative 9 would be negative 5, and then I could write that y to the negative 5th as 1 over y to the 5th. So my answer is 4x squared over y to the 5th power. Again, I had to have positive exponents. Let's see, let's clear the screen to do part B. So in B, I have notice that the first thing that my eyes are focusing on is I have a power that's being raised to a power. And the power I'm being raised to is negative second power. So I'm going to rewrite that first bit as 1 over 2y squared, and then this whole thing is squared. So you can see that's how I deal with a negative exponent, right? Those factors, there's 2 of them, of 2y squared, belong in the denominator. Now I have still this 8x squared y to the 7th, and I might go ahead and put it over 1 because I can combine these at some point. So let's take a look at this denominator in the first chunk here. That thing's getting squared, right? That's 2y squared squared. I need to multiply a 2y squared times another 2y squared. And sometimes, for convenience, you might want to just multiply it out. This is equivalent to 2 squared times y squared squared. But when I look at that, you can see I've got the 2 times 2 is a 4. So there's a 4 in my denominator. And then y squared times y squared is y to the 4th power. The other thing that I can do right now is I'm going to go ahead and, let me write this one just one last time. 8x squared and then y to the 7th. And that has a denominator of 1. So if I combine these now, in my numerator, it is 8x squared y to the 7th, and in my denominator, I've got 4 y to the 4th power. So you can see that I have a couple things I can simplify, right? There are some quote-unquote giant 1s lurking here. One of them is 4 over 4, right? So in fact, I'll write it out. I've got a 2 times a 4, and my denominator, there's a 4. So there's a giant 4, right? My numerator had an 8, which is 2 times 4. My denominator has a 4. Then I've got an x squared. And then I've got a y to the 4th in the denominator, and I'm going to write a y to the 4th in the numerator. When I do that, I'm left with 3 more factors of y in the numerator. That's y to the 3rd, right? Y to the 4th times y to the 3rd is y to the 7th. So you can see that there's some definite giant 1s here, 4 over 4 and y to the 4th over y to the 4th. So what I'm left with is a 2 and I'm left with an x squared, and we're also left with y cubed. So this is our answer, 2x squared y cubed. All of my exponents here are positive. This is the third and final question from page 1 of the student team test. Solve each of the following equations for y. I'm going to begin a couple of things I could do. I could, if I wanted to, divide both sides by 2. I can see on the left-hand side there's only one term, right? It's 2 times another term that actually has 2 terms in it, but it's just one term by itself. But I think what I'm going to do instead is I'm going to go ahead and use the distributive property and remove the parentheses on the left-hand side. So if I do that, I do have the 2 times 6, which becomes a 12. That pen is too large. Let me get a smaller pen here, and let me clear that. 2 times 6 is 12, and then 2 times negative 2 is minus 4y. On the other side, I have a positive 4y and then a negative 8. Now, oftentimes, I've seen students inclined to look at this and say, hey, both sides have a 4y. One's negative and one's positive. They cancel. Well, in fact, they do not. And in fact, what I'm going to do is I'm going to add 4y. And when I do that, this side will have no y's left. It'll have a negative 4y and a positive 4y. That will cancel. I need to add a 4y on the other side to keep the equation in balance. When I do that, on the left-hand side, we have just the plain old 12 now. On the right-hand side, we have 8y and then minus 8. So you can see it didn't actually make it equal to 0. Now what I'm going to do is I'm going to add 8 to both sides. And in the act of adding 8, this becomes 20, and that will equal 8y. And then finally, I'm going to divide both sides by 8. So y is going to equal 28, and probably I would be happy to call that, I could call it 10/4, and I could also call it 5/2. So y is the number 5/2. Now I'm going to go along and I want to check that real quickly. So I'm going to plug 5/2 into this equation. And I'm just going to do this right up here at the top. This is a check. So if y is 5/2, then I should have 2 times the quantity of 6 minus 2 times this 5/2 that I think is a solution. So that's one side of the equation. If I simplify it, it's 2 times 6 minus 5, because negative 2 times 5 is negative 10, and negative 10 divided by 2 is negative 5. So I have 2 times a 1, which is equal to 2. So over on the left-hand side, when I plugged it in, that was the number 2. Let's do the same thing for the right-hand side. So we think that it's equal to the following: 4 times 5/2. And let's see, 4 times 5/2, and then minus 8. Well, let's see, 4 times 5/2 is 20 over 2. 20 divided by 2 is 10. So what I have here is 10 minus 8, which is 2. And we can see that on both sides, we did indeed get 2, right? The left and the right-hand side both were 2. So y equals 5/2 is indeed the solution to this equation. Let's go ahead and take a look at part B. Let me clear the screen. Part B says, again, solve for y. So you can see this is the variable we're trying to solve for. And if I'm isolating this y, I guess the first thing I'll do is take away 8x from both sides. So that gives me that, I don't know why I'm writing, that gives me that 10y is equal to negative 8x plus 12. And now we're going to divide both sides by 10. So y equals, you can see that there are 2 terms on the left-hand side, and both of those terms need to be divided by 10. So I have negative 8 over x, I'm sorry, negative 8x over 10, and then plus 12 over 10. And then by a bit of simplification here. Let's see, 8 over 10 is 4/5. We've got minus 4/5 x. Be very careful, that's minus 4/5 x. And then 12 over 10 is the same thing as 6/5, so plus 6/5. So this I can't plug in to check that I'm correct, so I might go through slowly and kind of make sure I did it all correctly. One of the things I could do at the very beginning is divide everything by 10, and then I could subtract this x term over to the other side, but I'm pretty sure this is correct. However, you might want to just go through each step and see if perhaps, maybe somewhere along the way, Mr. Roberts made a mistake. Create a table, graph, and equation for the following sequence. This sequence, as I move from the first term to the second term, I could get from 4 to 8 by adding 4. If I try that for the next jump, though, 8 plus 4 more would be 12. And that's not what we have. We've got 16. So what's happening here is we're not adding 4 each time. We're actually just doubling. 4 times 2 is 8. 8 times 2 is 16. 16 times 2 is 32, etc. In fact, the next 3 terms there would have to be doubling. That would be 64. And then we'd have 128. And then we'd have 256. So if I was to create a table of values, right, this is, I guess this is n, the term number, and then this would be t of n, the value of the sequence at that point, right, the value of the term at term number n. And I put my term numbers, we begin with the first, second, third, fourth, fifth, and sixth term number. My first was 4, and then I went to 8, 16, 32, 64, and we end with 128. So I need to scale this so that I'm getting close to 128. It'd be nice if I could get to 256, but I want to try and maximize the use of my graph paper here. And I don't know that this is perfect, but I'm going to say every 2 lines are worth 10. So that's going to be a 10, a 20, 30, 40, 50, 60, 70, 80, 90, and then all the way up at the top here is 100. So that's t of n, that's the output of this function, right? That's the number in that particular term. And if I move forward here, here is the first term. I guess I'll count by, I probably can count by 3s. Let me do that. So I'll say the first term is here 3 over, and then 1, 2, 3. This is the second term, 1, 2, 3. Third term, 1, 2, 3. Fourth term, 1, 2, 3. Fifth term, 1, 2, 3. Sixth term. And that's good because I have 6. Hey guys, when you're setting up the axes, it's important to remember that these numbers tell me that I have to be able to accommodate a minimum of 4, right? And a maximum of 128. But I don't count by these numbers. I'm not going to write down 4, 8, 16, 32, 64. The spaces in between these have to be equal. So that's 10 units. From 20 to 30 is 10 units. From 40 to 50 is 10 units. From 60 to 70 is 10 units. So all of these are 10 units apart. And down on my bottom axis there, which is the term number, I guess it's n, every single one of those lines is worth 1/3. So you can see I've got 1/3, 2/3, and then 3/3, which is the number 1. So it's important that the spacing be equal and that it's very clear what your scale is. So you can see on my up and down scale, every single line is 5, or 2 lines is 10. And along the bottom, every single line is 1/3. 3 lines would equal 1. Now we need to come up with it says, right, the explicit formula. And what we're missing here is our 0 term, right? So the 0 term, if I was to go, as I go forward, I'm doubling, right? 4 times 2 is 8, times 2 is 16, times 32 is 64. 32 times 2 is 64. If I wanted to go and get the 0 term, I'd have to go backwards one. So going backwards on this list, I'm dividing by 2. So to get my 0 term, I'm just going to take 4, my first term, and I'm going to divide by 2, which would give me my 0th term would be the number 2. Now, remember, And in a geometric sequence, and that's what this is, right? The the value of the nth term is equal to, I believe our book uses the variables a times b and then raised to the nth power. So what do these mean, right? A right here is the zero term. And I don't, zero, I've been trying to write 0th, but it's the zero term. That's not part of the sequence, right? Because our geometric sequences and arithmetic sequence begin with the first term. We don't have a zero term, but in order to write the equation, it's helpful to consider what the zero term would be if you went back one. So this value of a is the zero term. So for this particular problem, my zero term we've said is the number 2, right? It's right up above there. B is my generator, what I'm multiplying by each time. And because I'm multiplying by 2 each time, my generator is 2 also, because every single time I'm doubling to get to the next term. So the explicit formula for this sequence is T of n is equal to the zero term 2 times 2 raised to the nth power. And if you were to spot check it and just consider a couple of them, for example, the fourth term, when I put in that n is 4, I get the following. I get 2 times 2 to the fourth power. Well, 2 to the fourth is 2, 4, 8, 16. So this is 2 times 16, which is indeed 32, which is what it should be. So this is producing the correct values. And then I need to plot the data too. It says plotted also. So I guess I'll use, this is a nice green color. Let me get some bigger dots here. So if I was going to plot these, the first term has a value of 4, which is, just below the number 5 there. So that's kind of a close representation of it. The second term is 8, which is below the 10. I'm going to put that dot below the 10. The third term, I'm up at 16. So here's 15. 16 is right above the 15 line. The fourth term is at 32. So there's 30, and then above that a little bit is 32. The next line would be 35. The fifth term is 64, so I got to come way up to right about there, just below 65. And then finally, the last data point I have, the sixth term is 128, which is actually off the graph, right? It's somewhere up this way, and it would take several more lines to accommodate that, but there's another one up there. Again, with sequences, arithmetic or geometric, we're not connecting these dots because we're keeping track of term numbers, the value of the first term, the second term, the third term, etc. We're not looking at the points in between. They don't really make sense when we're thinking about a sequence. So that's question number 1 from test 2. Dorothy is having a rough day, and she's just sitting around thinking of 2 numbers. So that's what she's doing. She's thinking of 2 numbers. That's what I always do. If it's a rough day, it's just sit around and think about a couple numbers. And she says to herself, hey, you know what? If I have these 2 numbers and I add them, I get 40. So the sum of the 2 numbers is 40. Now, I'm just going to say, I'm going to say let x and y be Dorothy's numbers. And her name is right there. It's spelled D-O-R-O, Dorothy's. That's interesting. Possessive with a Y ending. And a name, too. Let's say X and Y be Dorothy's numbers. So the first thing that she's got here is that, hey, the sum of the numbers, right? If I add them, X plus Y, she gets the number 40. And then she says, and the difference is 6. The difference between her 2 numbers is 6. So I don't know. I'm just going to like x minus y, right? To me, that's the difference between 2 numbers. X minus y, the difference between her numbers is 6. So you add them, you get 40, and they have a difference of 6. What are the numbers? It says write a system of equations and use the elimination method to find the 2 numbers. Write your solution as an ordered pair. Well, this is so nice that they're asking us to use elimination because as it turns out, my y variable will clearly be eliminated, right? I've got a negative y and a positive y. So when we add those, they're going to be gone. So on the left-hand side, we have an x plus another x, which is 2 x's. And on the right-hand side, we've got 40 plus a 6, which is the number 46. Now, if I divide by 2, right, x has to equal the number 23. So there's one of Dorothy's numbers. Now, we know that when she added her two numbers, she had to get 40. So if that's one of her numbers, then if I was to take that 23 and add y, I would get the number 40. So that means I could go ahead and subtract 23 from both sides. Oh dear, arithmetic. 40, and I'm going to take away the 23. 10 minus 3 is 7, and 3 minus 2, because I borrowed one, right? I borrowed one here. So 3 minus the 2 is the 1, so I get 17. So apparently if I add 23 and 17, I get Dorothy's numbers of 40, wait for it, and the difference between these numbers is 6. So if I take the 23 and I subtract 17, oh yeah, if I subtract the 17, 13 minus 7 is indeed 6, and I borrowed 1 there. So I do get a difference of 6. So her numbers are 23 and 17. Now it does say write your solution as an ordered pair. I happen to pick x and y, so it makes my ordered pair kind of nice. If you didn't, it may make it difficult, but I would say that my solution is 23, 17. X is 23 and y is 17. Have a good afternoon, Dorothy. Okay, on this question, as I looked at some of your answers, I saw evidence for why I think it is a good idea to forget, for a while anyways, to forget this shortcut that if you've got like if you've got 2 over 5 equals 6 over x, right? If you've got this situation where you have a proportion, right? I have a ratio equal a ratio. One of the things that you guys are quick to point out is, hey, you can just cross multiply, and the cross products are equal. Well, that is true. And the reason why that's true is I could demonstrate that that's true by using a technique that I think is more useful called fraction busters, right? So if I was to multiply both sides of this equation by 5 first, on the left-hand side I would get 2 times 5 over a 5, bust the fraction, right? And over on the other side I'd get 6 times 5, over an x. So this becomes 2 equals 30 divided by x. The next thing that I would probably do to bust the fractions is I would multiply both sides by x. So now all of a sudden I've got 2x equals 30x over an x, bust the fractions, right? So I get that 2x is 30, and haha, this is where you guys say, yeah, look at this is what we were talking to you about, Mr. Roberts. 5 times 6 is 30, and 2 times x is 2x, right? So now you can see if you divide both sides by 2, you get that x is equal to 15. I totally get it. I'm tracking, and that works. However, here's what happens. We come along, and this is very specific, right? This is applying to a proportion. One ratio equals another ratio. And then all of a sudden, we look at a problem like this, and we try to do something quite similar. And I saw a lot of variations with this where you were trying to like, maybe I can multiply these, or maybe this product. And it just got just messy, right? Look, get a clean glass of water, just clear water, nothing in it, no ice cubes. Just take a sip of that beautiful clean water and let all this go away. No confusion, no need for it. What we're going to do is just use fraction busters. So let me clear all of this stuff off to the left. So in order to use fraction busters, if you look at this, I've got a denominator with a 2, a 3, and a 6. And it turns out because 6 is actually 2 times 3, if I multiply both sides of this by 6, it should bust all of these fractions up, right? I'm not going to have a single fraction left. 6 is the least common multiple of 2, 3, and 6. So I suggest that that's exactly what we do. We're going to multiply both sides of this equation by 6. So when we do that, first thing that we encounter here is we're going to have a 3 times an x times a 6 over 2. Notice I just added a factor of 6 to that numerator, plus 2 times a 6 over 3. And you may be saying to yourself, hey, Mr. Roberts, how come you're not putting a 6 down in the denominator? I don't want to do that because then I'd be multiplying by 1. I'm actually multiplying every single term by 6, or 6 over 1 if it's more useful. And then over here on the next side, I'd have a x times a 6 over a 6. Well, the first thing you probably point out is that, hey, that clearly is a busted fraction, right? And over on that side, we just have x now. And there's more here, but you may not see it quite yet. So let me rewrite this one more time here. This is 3 times x times 2 times another 3 all over a 2, plus a 2 times a 2 times a 3 over a 3. And over here we've got just x now. So now that I've done that, you can see, the giant 1, if you will. There's that busted out fraction, and here's a 1 busted out fraction. Not a very giant 1 actually, but clearly I've got a 2 over 2. There's a common factor there, so that's just the number 1. 2 divided by 2 is 1. So what we end up with on the left-hand side, we've got 3 times x times a 3, which is 9x, and then plus 2 times 2, which is 4, and that equals the number x. So as we said, hey, we just multiplied everything by 6, and our fractions are completely busted. So now let's go ahead and clean this up. And I am going to do it this way. I want because I think it's instructful to see this. I'm going to take away an x from both sides. And when I do that, this side becomes 8x plus 4. But don't forget, the right-hand side is the number 0. I've seen a lot of students write that down. They'll write 8x plus 4, and they're like, what the heck? There's no equation anymore. Yeah, there is an equation. We just took away the x from the right-hand side. X minus x is 0. So that's what we've got. Now I guess I can take a 4 away from both sides. When I do that, we get that 8x is equal to negative 4. And then finally, I'm going to divide both sides by 8. So x is equal to negative 4 over 8, which does have a giant 1 of 4 over 4. And it's just the same thing as negative 1/2. So x is the number negative 1/2. And it's actually kind of fun to plug that in if you've got a calculator handy. You know that's the same as negative 0.5. But plug it in 3 times negative 0.5 over 2 plus 2/3, and then compare that to negative 0.5 over 6. Anyways, that is question number 3. Oh, if I had $1 for every time this happened, right? Margot was doing her homework when her dog bit off a piece of the paper, and she had left. All she had left of the sequence was terms 1 and 5 shown here. So she only knew that this term was term 1 and over here was term number 5. First question is, could this sequence be arithmetic? If so, what is the equation? What is the equation? And fill in the missing terms. Well, let's see here. You know what? If I've only got 2 points, absolutely it can be arithmetic, right? Because I can find the slope and I can find the y-intercept and I can make the equation that'll fit that. And not only that, I'll be able to figure out what she's adding each time. So actually that's good practice. Let's go ahead and do that. Let's find the slope and y-intercept. So I guess these would be like my y values and my term numbers would be x's. So if I look at my change in y, I could look at 64 minus 4. And my change in x would be 5 minus 1. 64 minus 4 is 60. And 5 minus 1 is the number 4. And let's see. If I divide 60 by 2, I get 30. And if I divide that by 2, I get 15. So it looks like my slope is the number 15. Now, if that's my slope, I need the y-intercept, and I could actually get the y-intercept two ways, right? That's the 0th term, so I can take the 4 and subtract 15, and 4 minus 15 to get the 0 term would be negative 11. That should be my y-intercept. I can also get it this way, right? Y equals mx plus b. I know that if I'm going to go ahead and use this point. If 4 is my y value, so I've got 4 equals, and then my slope we said was 15, and my y-intercept is, and my current x value here for this point is 1, and then plus b. So you can see what happens, right? I'm having to solve for b. I'm going to take 4 and subtract 15. I'm going to subtract 15 from both sides of that equation, giving me that b is exactly what we said it would be, negative 11. So I've got the slope of 15 and the y-intercept of negative 11. So I'm ready to write the equation. So yes, this could be arithmetic. Like add 15 each time and it'll work quite nicely. You'll get to 64. So the equation would be y equals 15x minus 11. And fill in the missing terms. It says, okay, so if I'm filling in the missing terms, 4 plus 15 would be 19. So I'll write this here in green. This is a 19. And 19 plus 15, oh dear, got to do arithmetic. 19 and 15, it's a 4. Carry the 1 is 34. And then I got 34, and I need to add 15 to that. That's a 9. That's 49. And then one last one, just to make sure. 49 plus 15 should land me at 64. And 9 and 5 is indeed 14. Carry the 1, and I got 4, 5, and 6. Yeah, it's 64. That's perfect. So my missing the missing terms would be 19, comma 34, comma and 49. So yeah, it definitely could be arithmetic. So that's part A. And I got a lot of junk in here, so let me clear the screen and we'll go on and do part B. So gone. Part B, could the sequence be geometric? Ooh. If so, what is the equation, and fill in the missing terms? I'm pretty sure if I just have two terms, I could make it either arithmetic or geometric. You know, I don't have, if I've only got two pieces of data, I think I can make two pieces of data fit either. So the question is here, what does it appear that I'm multiplying by to get up? And I have a feeling, and I'm going to try this anyways. If I double this, this is 8. Double that, that's 16. Double that, that's 32. And if I double that again, it's at 64. So I can say, yeah, this could be geometric. Yes, this could be geometric. And I definitely know that my multiplier, right, my generator is multiply by 2. Now, what's the 0 term? Well, if multiplying by 2 is taking me forward, I need to divide by 2. So my 0 term would be equal to 2. 4 divided by 2 is 2. So this would look like this. Y equals my 0 term times my multiplier, and then to the x power. Now, I wrote that as a y equal equation. I could use it with sequence notation if I wanted to talk about term numbers n. The number of the term is n, and the value of that term is t of n. But we'll just leave it like that. If you wrote something like this down on your paper, t of n equals 2 times 2 raised to the n power, that's obviously correct also. So, all right, keep the dog away from your homework. So one of the things we talked about earlier on in the year was this method of solving equations you might consider called the look inside method. And if I look inside of this radical, the radical is 6x minus 2. But the important thing is when I take the square root of that, I'm supposed to get the number 8. So my thinking is, well, the square root of what number gives me 8, right? And it is the case that it is the square root of 64 that gives me 8. So what I'm thinking here is if the square root of 64 is what gives me 8, that means that this thing, right, looking inside, this 6x minus 2 must equal the number 64. And to solve that's pretty straightforward, right? I'm going to add 2 to both sides, so this is now 66. And I'm going to divide both sides by 6, so x is 11. So when I plug 11 in, notice what I get. I get 6 times 11, and then minus 2. And I'm having the square root of that. That's 66 minus 2, which is 64. And the square root of 64 is indeed equal to 8, so it definitely checks, right? Square root of 64 is 8. Claudia works at a sweet shop, not a sweatshop, a sweet shop making chocolate dipped bananas. Sometimes she drops the chocolate dipped bananas before she can get them to the freezer. Claudia earns 20 cents for every frozen banana that she makes, and she loses 5 cents for each frozen banana that she drops. Last Wednesday, Claudia dipped 48 frozen bananas, but not all of them made it to the freezer. She earned a total of $7 rather and 60 cents. How many bananas were dropped and how many made it to the freezer? So first of all, it says define your variables and write a system of equations that represents this situation. So I'm going to say whoops, that's too fat of a pen. Let's see. Let me make that a little bit thinner. So let m equal the number made and frozen. So these are the ones that she gets paid for, right? They made it into the freezer. She made them and they froze them. And I'm going to let d equal the number dropped. So these ones did not. They were dipped in chocolate, but then they fell on the floor, and you can't sell that. So they were made but not frozen. So one of the things I know is that she dipped 48 of them in the chocolate, right? But not all of those made it into the freezer. So one of my equations, I could say, hey, the number that were made and frozen plus the number that were made and then dropped equals 48 bananas. Another equation that I can write relates the amount of money that she earned. We know that for every single one of them she made and froze, she earned 20 cents. So I could say 0.20, 20 cents for every banana that was made. And then it says that she lost 5 cents for every banana that was dipped in the chocolate but then dropped on the floor. So minus 0.05, that's 5 cents for every banana that was dropped. Now, if I add that up, the 20 cents for all the ones she made minus the 5 cents for each one she dropped, she earned a total of $7.60. So this is a system of equations, and this is what we'll work with. Probably the first thing that I would do is I don't like dealing with these decimals, so I'm going to multiply both sides of the second equation by 100. And if I do that, the decimals will go away, right? 0.20 times 100 is going to be the number 20. 7.60 times 100 is going to be 760. So I'm going to multiply both sides, all the terms, by the number 100. When I multiply that first term on the left-hand side by 100, I get 20m minus, let's see, 0.05 times 100 is 5d, and that equals 760 pennies. These aren't dollars now. So let's see, the other equation that we had was m plus d is equal to 48. So looking at this system, I'm going to choose to solve it using elimination. You could go other ways just as easily. But what I'm going to do is, I believe, multiply the second equation here by a positive 5. And if I multiply that equation by a positive 5, my d's will cancel. So I'm going to rewrite them again. Let me rewrite the first equation first. So I've got 20m minus 5d is equal to 760. And the second equation, multiplying by 5, I've got 5m, and then let's see, that would be plus a 5d, and that would equal 48 times 5. 48 times 5 is 240. And now this is a great system for solving via elimination, right? If I add them, I get 25m plus 0d. The d's cancel, thus the term elimination. I eliminated that variable. And when I add 760 and 240, that gives me 1,000. Wow. So that means that m is going to equal 1,000 divided by 25, or m is equal to 40. So she made, that is, dipped in the chocolate and got into the freezer 40 bananas, and she oh, there's the bell. Sorry, class. And she dropped. Let's see. If she made 48, she had. That means she dropped 8. So d equals 8. So she made a total of 40 frozen chocolate dip bananas, and that means made it into the freezer. I guess I should be careful. She made 40. She made 40. She made 40 of them, right? That she could sell. That could be sold. And then, of course, the bad news is that 8 of those, and this is sadness, right? 8 were dropped on the floor. So they were dipped in the delicious chocolate, but you couldn't sell those things because they had, whatever's on the floor that's just disgusting sounding. 7 dipped and dropped. Does dropped have 2 P's? I'll look that up sometime. Anyways, that's question number 3. Find the equation of the line through the points 4, -5, and 8, -2. So each one of these points has an x value, right? X is 4, and x is the number 8, and they both each have a y value also, right? In one case, y is -5, and for the other point, y is -2. Now, in order to find the equation of this line, I need 2 pieces of information, right? If I'm considering y equals mx plus b, I need to know both the slope of the line, and I'm also going to need to know the y-intercept of the line. And both of those pieces of information are going to be pretty straightforward for us to find. So we're going to go ahead and set out, first of all, by finding the slope. And of course, the slope through any 2 points is how much does y change divided by how much does x change, right? It's the change in x divided by the change in y. And change is always, if I say, hey, I'm going from 5 to 7, how much did I change by? Well, 7 minus 5 is 2. That's a change of 2. If I'm going from 3, and I could put this on a number line way down here. If I'm going from 3 to a -5, how much did I change there? Well, 3 minus a -5 gives me a change of 8, right? So change, again, always involves this subtraction, right? 3 minus, and then the other number, -5. So in each case here, the change in y, I'm going to have a subtraction in the numerator, and I'm going to have a subtraction down in the denominator as we calculate the change in x and the change in y. So first of all, let's do the change in y. That's what goes in my numerator. And you can see y ends up at -2, and it was over here at -5. So I'm going to say my y is changed by -2 and then minus a -5. So from 1, the -2, I'm going from the second point first, -2, and then to the minus -5. Same thing for the x. It's important since I started my y's, my change in y's with the second point, I need to do that with the x also. So I'm going to start x at the 8, right? What's the change between 8 and 4? So I'm going to say 8 minus the 4. So x value is increased by 4. So let's go ahead and simplify this, right? So this equals something else. Up in the numerator, I've got a -2 minus a -5. Well, -2 minus -5 is -2 plus 5. So I'll write -2 plus 5. And then down below, 8 minus 4 is 4. I'll just write this one last time. -2 plus 5 is a 3, and then 4. So my slope in this case is 3/4, up 3 over 4. Now what I need to do is I need to find our y-intercept, right? We've got the slope. It's taken care of. This value, the slope, is the 3/4. Now we need to go ahead and find what the y-intercept is. And once we've got the y-intercept, we can write the equation of the line. So let's find the y-intercept. Well, the y-intercept we're going to find by just using this equation, right? Y equals the slope that we just found, 3/4 x plus b. And we're looking at it like, well, that's not getting us anywhere, except we happen to know 2 particular points that are on this line, right? And it doesn't matter which one we use. We could use either, but these 2 points, right, provide us with an x and a y in the context of this line. So I'm going to go ahead and use the first point there, and my x value is 4 and my y value is -5. So I'm going to go ahead and write this as -5, right, that's the y value from that point, equals 3/4 times the x value of that point, which is a 4, and then plus b. Well, when I multiply 3/4 times 4, I end up just getting plain old 3. And over here I've got a -5 still. And then to get b, right, I'm just going to subtract 3 from both sides. So take away 3 here, take away 3 here. So that gives me that b is equal to -8. So we now have both the y-intercept and we have the slope. So we can write our answer, right? Our answer is y equals 3/4 x and then -8. Now, this equation should satisfy both of the points, and I've got a pretty good idea that it satisfies the first one because I generated the y-intercept by plugging it in. But just to be sure, I'm going to go ahead and, in my mind at least, say, hey, let's let the x be a 4 and the y be a -5. And when I do that, it becomes 3/4 times the 4 is 3, and 3 minus 8 is -5. So that does check. And then I want to try it with the other point where x is an 8 and a y is a -2. Well, if I do that, let's see, that's 3/4 times an 8. 3 times 8 is 24/4, which is just plain old, it's plain old number 6. So what I get here is I get 6 minus 8, and 6 minus 8 is indeed -2. So 6 minus 8 equals -2. So for sure, that equation, y equals 3/4 x minus 8, definitely contains both of those points. It contains the first and the second points. So that's our solution. So this next equation, or this next problem, actually it's repeated twice, and I don't know if this is a typo, just if it was on the test this way, or if it's just a typo when I put things and set them up here. But oh no, it's actually different. I'm sorry. In one case I'm solving for b, and the other case I'm solving for y. So these are different questions. Very good. So for the first one, a, if I want to isolate b, right, all I've got to do is I've got to take away ay. So I'm just going to subtract a times y from both sides, minus a times y. So that gives me the x that I had minus ay And that is what b equals, right? So again, I took away the product of a and y from both sides. The left-hand side already had an x, so it's an x minus the product of a and y. For the next one, we need to isolate y. And to do that, I'm going to begin by taking away b from both sides first. So I'm going to take away the b. So on the left-hand side, I've got x minus a b, and that equals the product of a and y. And then to get y alone, what I'm going to do is essentially make a giant 1 on one side by dividing both sides by the a. So you can see this is a giant 1. A over a is 1. So I end up getting that y is equal to x minus b over the a. Right? It's the x minus b over a. That's what y equals. So that is problem A and B. Question number 2.
Okay, finish the table and find an equation for each of the following sequences. There's 2 here, there's A and B. In the first one, I'm going from 36 down to 27 down to 18, and then down and down. It's interesting that this top n value is missing, but I'm assuming that this is value 1 and 2 is value 2. This is value 3, and then I've got 4 and 5. And as I move down here for the first value, right, 36 minus 27, I believe is a 9. Yep, so this is minus 9. And 27 minus 9, oops, is 18. 27 minus 9. And then if I take, so that is minus 9. And if I take the 18 and I subtract 9 again, I'm at 9. And then 9 minus 9 should put me at 0. So you can see this is, because I've got a common difference, right? I'm decreasing by 9 each time. This is arithmetic. And part of it, I know for a general arithmetic sequence, y equals mx plus b. This m value is what I'm adding or subtracting in this case each time. So m is negative 9. And b is my 0th term. Now if you look, the first term, the first legitimate term in the sequence is 36. And to go forward, I'm subtracting 9 each time. So if I want to back this up, I would take 36 and I would add 9 to it, which would give me 45. So my 0th term is 45. So the equation for this sequence should be y equals negative 9 times x and then plus 45. The next sequence, however, it does start with 36 again, but I could say, hey, 36 minus 18. Let's see, 36 minus 18 is not 46. 36 minus 18 is 18. But then if I subtract 18 again, I would be at 0. So it can't be that I'm subtracting 18 each time by 18 each time. So instead, let's consider 36. What's half of that? It's 18. And half of 18 is 9. Okay, so what's happening here is each time I'm multiplying by 1/2, right? So my generator is times 1/2. So if I went to the next one, the next term would be 1/2 of 9, which would be 9/2. And then 1/2 of that would be actually 9/4. So this is a geometric sequence. And the general form of a geometric sequence is y equals a times b raised to the x power. A is my 0 term, and b is what I continue to multiply by, right? Each time I'm multiplying by 1/2 for this one. Now for the 0 term, let's see, if I go forward in the sequence, 36 to 18 to 9, each time I'm multiplying by 1/2. So if I want to get the 0 term, I'm going to do the opposite, and instead I'm going to multiply by 2. And that gives me my 0 term is the number 72. So this would be y equals 72 times 1/2 raised to the x power. The one thing that I don't think I'm going to do here is graph this, right? I think you guys can scale the graphs and plot those points. So I do encourage you to use as much of the space as you can. So think about scaling the graphs appropriately. Another thing is when you scale them, please do not just look at the values in your table and just increase by those numbers. For B, you should not be going from 0 to 9 to 18 to 36. It has to be a consistent numbering. But we're going to leave this question here.
Okay, so the last page, all of you did this page, and it says below are 3 systems of equations and 3 methods of solving them. That they're not listed here on this slide, but you had them listed on the back page. It says, and by the way, the three methods were the equal values method, elimination, and substitution. And it says solve each system in a different way. Make sure you use all 3 ways, show all your work, and record your answers as a coordinate pair x and y. By the way, on A, I didn't like it how this had an M and an N in it. That will not happen on the test. They will all have x, y values so that you can do coordinate pairs. But this show all your work is extremely important. And you guys watch me do work enough, you hear me do it, you see it, that you know the types of things that I'm looking for that you need to include, just so you're real thorough and there's no guessing, poof, magic happened and then we're here. So looking across at these 3, I would say that probably I'm going to use this one. I'm going to probably solve using elimination. And I'm thinking probably the next one, I would probably solve using substitution. If you look at it, this thing right here, that is a very nice substitution for y in the second equation. So we'll do that on the next slide. We'll solve that using substitution. And then the last thing over here, we'll probably solve this one using the equals value method, because if you look at it, the first equation tells me that that is x, and the second equation tells me that this is also x. So I'm just going to set those 2 x values equal to each other, solve for y, and then use that value of y to find x. So let's begin, and we're just going to do A on just this slide. So let's start with A. So it says, I said that we're going to solve this using elimination, and you can see one of the challenges we have is that none of the variables will actually eliminate if I add these equations. I'm going to get, I would get 8m plus 4n equals negative 12. To fix that, it's not a big change. We're just going to multiply one of these equations through by a negative 1. And I'm going to choose to multiply it through the top equation by negative 1. So I'm going to rewrite that equation below. Instead of a positive 5m, it's going to become negative 5m and then minus 2n, and that will equal positive 10. And then right below that, I'm going to write the original second equation, which was simply 3m and then plus 2n, and that equals a negative 2. So as you see, I have equal things from the first equation, right? The first equation tells me that 5m minus 2n is equal to 10. And in the second equation, I'm told that 3m plus 2n is equal to negative 2. So what we're doing here is I'm adding equal things to both sides of the equation, to the first equation. And as I do that, my n's values will cancel out. So if I was to combine those, right, on one side I'm adding 3m plus 2n, on the other side I'm adding negative 2, but because they are equal to each other, I'm not changing the first equation. So let's go ahead and combine them. I get negative 5m and 3 is a negative 2n. When I combine negative 2n and positive 2n, that's gone. And over here I've got 10 minus 2, which is 8, positive 8. So that means that m has to equal 8 divided by negative 2. M has to equal negative 4. So we know m. Now we need to set out and find n. And to do that, it doesn't matter which equation we start with, but probably we should use one of the two original equations. So I guess I'm going to go ahead and use the second one. So I'm going to say if I have 3 times this newfound value of m, right, 3 times negative 4 plus 2n, I should get the number negative 2. So again, that's just me taking that second equation, writing it here with the value of m that we found. 3 times negative 2 is negative 12, plus 2n equals negative 2. I'm going to add 12 to both sides, and when I do that, I have that 2n is equal to 10, therefore n is the number 5. So I think I found it. Now, before I go on, I just want to double check. I'm going to plug these numbers in and make sure both of the equations, make sure that it works. So in the first case, I'm going to multiply 5 times, I think this is negative 4, so that would be a negative 20. And then plus 2 times a 5. 2 times a 5 would be a plus a 10. And yeah, sure enough, when I combine a negative 20 and a 10, I do get a negative 10. And that's what I had on the other side. So it definitely checks in the first equation. And I'm pretty sure it checks in the second equation. 3 times negative 4 is negative 12. And to that, I'm going to combine 2 times 5. 2 times 5, which is 10. And when I combine negative 12 and 10, I do get negative 2. And that's exactly what I had on the other side. So that solution, m is negative 4 and n is 5, satisfies it. Now, as an ordered pair, you could go alphabetical if you wanted, right? L, M, N. So you could list this as an ordered pair as negative 4, comma 5. But typically, if it's not an x and a y, we're talking about xy ordered pair, I'm fine with you just leaving it as m and n. So that is, we did the first one using elimination. Now we're going to set out and do B using substitution. And as we pointed out before, this value, right, negative 3x plus 6 is exactly what y is. So we're just going to rewrite that second equation using this replacement value for y. So that we will have 6 times the value of x plus 2 times the quantity of negative 3x plus 6, and that will equal 12. So again, all we've done here is we've taken a value that's equivalent to y from the first equation and placed it in the second equation. Using the distributive property, we have 6 times x plus a negative 6x plus a 12 equals the number 12. That's interesting because 6x and then minus 6x is 0. This equation collapses to 12 equals 12, which makes me think that these lines are probably identical lines. And what we're looking at here is, I don't think, no, they're not parallel lines. They're identical lines. So what we would say is that any xy solution that worked in the first equation would work in the second equation too. And in fact, if I was going to demonstrate that, I could take away 6x from both sides of that, giving me that 2y is equal to negative 6 times x plus 12. And if I divided both sides by 2, that gives me y equals negative 3x plus 6. So I can see, yeah, these are actually the exact same equation. So there's an infinite number of solutions and I want to be a little bit more clear. Any xy pair that works in the first equation would also work in the second equation because they're the same equation, right? Sometimes I see some of you will write, oh, all real numbers? Well, no. And it's not all points either, right? It's only points that work in one will work in the other. And there's a lot of those points, right? That's why, in fact, there's an infinite number of those points. But saying that there's an infinite number of points and saying all points is different. If I'm looking at, and this is just a sketch, right? It has a y-intercept at 6 and a slope of -3. So if I'm looking at this line, there are clearly an infinite number of points on that line that make those equations true. Any point on that line would make it true. And in fact, I could look at points in between points and between those points, right? There's all kinds of points there. So there's an infinite number of points, but that's not all points, because this point right here and this point, yay, they're purple. That's exciting. Go Shasta. But those points don't satisfy the line, right? Those points are not on the line. So we would say that there's an infinite number of solutions, but not all points are solutions. And we certainly wouldn't say all real numbers, because if you've got a system of equations, real numbers aren't the solutions. Points are, right? And points require both an x and a y. All right, so let's look at the last one, C. So we said in C that we were going to use the equal values method. So that's exactly what we're going to do. Remember, we said that this is x, and according to the second equation, that is x. So we're just going to set those equal values equal. So 8 minus 2y, that's an x. You know what, actually, you didn't hear that. X is equal to x. So what I'm going to write is 8 minus 2y, because that's x from the first equation, and that's going to equal y minus 4. That's x from the second equation. So if I was to solve this, I guess I'd add 2y to both sides. So 8 is equal to 3y minus 4. Again, adding 2y to the left-hand side took it away, and then y plus a 2y on the right-hand side gave me 3y. And then finally, I'm going to add 4 to both sides. Not finally, almost finally. Add 4 to both sides. If I add 4 to the right-hand side, that -4 will go away, because -4 plus 4 is 0. But over here, I get a 12. So 12 is equal to 3y. And if I divide both sides by 3, I get that y is 4, right? Y is equal to the number 4. So that's one part of my solution, right? I know what y is, but I need to know what x is. Well, if I look at the second equation, it's pretty easy to see that 4 minus 4 is 0, so x would equal 0. And let's just check that in the second equation too. That says 8 minus 2 times y, and y is the 4. I wrote it there. So 8 minus 8 is 0. So in both cases, I did indeed get that x is equal to 0. So as an ordered pair, my solution would look like 0, comma 4, right? If I were to graph these two lines, they would intersect at the point x is 0 and y is 4. I'm not going to do all the questions from the individual test from Chapter 6, but there are several questions that I saw students missed consistently, so I think it would be a good idea for us to review those. So the first question that kind of fits that category is question 3b. And you can see that this is a monomial. There's just one thing here. There's no addition or subtraction that's defining additional terms. So I've got a single term, so it's a monomial. And there are several things that are making up this product. For example, there's 2 factors of x, then 3 factors of y. Then there's the number 7 itself, 3 factors of x. And then I have 6 factors of 1 over y. Remember, when we see a negative exponent, that indicates that it's actually division by that base. So that's 1 over y. I probably would choose to rewrite this the following way. I'd bring the 7 out front first, and then I'll just go ahead and write the x squared, the x cubed, then I'd write the y cubed, and then I've got this y to the -6th power. So if I look at it, I like to check and verify that I've brought everything down. And you can see I've gotten each of the pieces that are making up this product. The next thing I might now do is go ahead and use the fact that if I'm multiplying, if I've got 2 factors of x and 3 additional factors of x, that's a total of 5 factors of x. So I can rewrite this as 7x to the 5th power, and then I'll go ahead and write y to the 3rd. And I said that these factors of 6 here, this is y, factors of y rather, y to the -6th, is equivalent to me dividing by y 6 times. So if I was to rewrite this, I might put 6 factors of y in my denominator. Now at this point I can see there is a quote-unquote giant 1 um, in this problem. So I can write this 7x to the 5th, y to the 3rd. In my denominator, if I split those 6 factors of y up into a y to the 3rd and then another y to the 3rd, just for convenience, I can see that y cubed over y cubed is 1. So what I'm left here with is 7x to the 5th power, and I'm dividing by y 3 times, so y over y to the 3rd power. So this is the answer for 3b. Actually, that was 3a. This is 3b. In 3b, one of the key differences here is the use of parentheses with an exponent. So be careful when you see this. If I had 3x to the negative second power without the parentheses, that would be equivalent to 3, and then I would be dividing by 2 factors of x, or over x squared. In this case, I have 3x to the negative second power. I'm sorry, 3x in parentheses, and that's raised to the negative second power. So that's equivalent to 1 divided by 3x in parentheses squared. And if I've got 2 factors of 3x in my denominator, 3x times 3x, that's equivalent to 1 over 9x squared. Remember, this means I've got a 3x times another 3x, which is 9x squared. Now what I can do with that, I'm just going to go ahead and write this part, right? 3x in parentheses to the negative second power is equivalent to 1 over 9x squared. Now I'm going to be multiplying this by, and I'm going to write all of these in a numerator. So 27x to the 4th, y to the second power, and I can put this all over the number 1. Because it's equivalent to what's above, right? Dividing by 1 doesn't change things. Now, if I go ahead and rewrite this as one single fraction with one fraction bar, I've got 27x to the 4th y squared over 9x to the second power. And when you look at this, you can definitely see a couple giant ones, right? 27 is 3 times 9, so I've definitely got a 3 times 9. I've got a 9 over 9. That's part of the giant one. But also, if you look at the x squared, there's 2 factors of x in my denominator. And in my numerator, I can rewrite this as an x squared and another x squared. That's the x to the 4th. And then times y squared. So when I focus on this, right, 9x squared over 9x squared is present in both the numerator and denominator. That creates a giant 1. And with that factor of 1, right, multiplication by 1 doesn't change the value. So I can rewrite this now as simply 3x squared and then y squared. So when I have an equation that has fractions present in the denominator, one of the techniques I demonstrate often in class is fraction busters. By simply multiplying both sides of this equation, every term on both sides, by a particular value, you can eliminate certain fractions. And I could choose to do this kind of one piece at a time, or I could do it all at once. And to be honest, I like to do it all at once. So I'm going to go ahead and multiply both sides of this by 4y. And actually, I can write it as 4y over 1. Now, the reason why the 4y is the least common multiple of 2y and 4. And if that confuses you, it's okay to go ahead and multiply both sides by y first, and then multiply both sides by 2. And then you might have to multiply both sides by one additional thing to see where it gets. But, 4 is 2 times 2, and so I need 2 factors of 2, and I need a factor of y. So this should eliminate all the fractions. So if I was to rewrite this, I'll go ahead and write in my numerator, I've got a 3 over 4, and then I've got plus 2 over a y, and over here that equals 5 over a 2. And I'm going to bring in these factors of 4y, right? I've got a 4y here, and a 4y for that term. So both terms on my left-hand side picked up a factor of 4y. And over on the right-hand side, I'm going to bring in a factor of 4y. So at this point, right, if I simplify this, you can see that I'm going to eliminate fractions. So for example, in the first term on the left-hand side, there's a giant 1 of 4. On the next one over, there's a giant 1 of just plain old y. And then over from there, there is a giant 1. It's 4 divided by 2, is 2. So I think I'll just go ahead and write that in the answer. So this first part is going to be a 3y. That's what this term becomes, plus the number 8. And then over here that will equal, let's see, 5 times 4y is 20y, and 20y divided by 2 is 10y. So I've got 3y plus 8 equals 10y. Next, to solve for y, I would choose to subtract 3y from both sides. And if I do that, my equation on the left-hand side becomes an 8, and over on the right-hand side we have 7y. So I'm looking really closely at this, and I'm being very intentional here. I'm choosing to divide both sides by 7 because I know that that will give me a giant 1 on the right-hand side, leaving me just a single value y. And if I divide this side by the 7 over here also with the 7. So without kind of just guessing or jumping, I showed that step. And on the left-hand side, I have a y, and on the right-hand side, I have 8/7. So it's not what some of us consider a pretty answer, but y equals 8/7. And if you choose to, you can write it as 1 and 1/7. That's fine as well. So let's review this recursive definition and then writing the explicit equation from a sequence. So the first thing is Maddie's given a recursive definition for an arithmetic sequence. This particular sequence, you can see it says the very first term is the number 55. So when I look at this, I'm reading at this is that the very first term is 55. And then take a look at the next part. Well, so I can write that down, right? Because I'm supposed to give the first 4 terms of the sequence. So the first term is 55. And then it says the following. It says, look at the notation. In order to get the next term, in order to get the n plus 1 term, the one that comes after the term I'm at, take the term that you're at, take its value, and subtract the number 10 from it. So if I want to jump forward and get the next value in this arithmetic sequence, what am I going to have to do? I'm going to have to take the term that I'm at, in this case 55, and I'm going to have to subtract 10 from it. 55 minus 10 is 45. And then I just keep doing that same pattern. I keep subtracting 10. 45 minus 10 is 35. And then one more time, 35 minus 10 is 25. So you can see I have the first 4 terms of that sequence. I've got the first term is 55, the second term is 45, the third time is 35, and the fourth term is the number 25. In part B, we're asked to write the explicit equation for this sequence. Well, I know arithmetic sequences and linear functions are related to each other, right? The form of those explicit equations are very much the same. And there's a lot of ways I could do this. I could look at, for example, what's the slope, right? The slope, and I'll write this definition, is it's the change in the y values divided by the change in the x values. Now, if I look at just the first couple terms right here, when I go from 55 to 45, you can see that's equivalent to decreasing by 10, right? So I've got a change in y of 10. And when I go for my x value, when I go from a 1 to a 2, you can see that's an increase of 1. So my change in x is 1. So that means the slope of this is negative 10, right? And by the way, you can always see this value when you're looking at the recursive definition. Each time I minus 10, so each time I change x, my y values are going down by 10. So I know the slope. The other thing that I can do is I can just back this up 1 and find the 0 term. So you can see the first term is the number 55. And to go forward, I subtract 10. But if I want to know what the 0 term is, right, I could go ahead and add 10. So this right here, it's not part of the sequence, but it's the 0 term, right? The term before the first term. I can use that to build my sequence, my equation, and it would look like this, right? Using this notation, right? T of n, the value at any particular number in my sequence is equal to, let's say, I could say minus 10 times n, and then plus my 0 term, which is 55. And that's kind of a general rule, right? You see here your common difference is negative 10. I'm decreasing by 10 each time. And my 0 term is 65. The reason why this is called the explicit rule is if I just plug in any value n, for example, if I plug 4 into this function, it will give me that the value of that sequence at that point is the number 25. So for example, when I plug 4 in there, you can see this becomes negative 10 times the number 4, which is a negative 40. And if I have negative 40 and I add to that 65, I definitely get the number 25. So that is the explicit equation for this sequence. You plug in the term number you want, it tells you the value. Up above, we had the recursive definition. In order to get a particular value, you need to build out the entire sequence just by going each time just minus 10, minus 10, minus 10. All right, that's question number 6. Question 7, our textbook suggests this technique called the quote-unquote look inside method. I don't know if you're fond of that. There's other ways to consider this too, but I do know this. If I'm taking the square root of something and I'm getting a value of 7, I know because I know how to square numbers. I know my perfect squares. I know that this has to be the number 49. The square root of 49 is 7. Why that's useful is I know that the argument inside of the square root function here, right? The square root of 15x plus 4 must be the number 49 because I immediately take the square root of that and I get a value of 7. So looking inside, I'm saying, hey, this 15x plus 4 must be the number 49. Well, if that's the case, then that means that 15x must be the number 45. And if I divide both sides of this by 15, I get that x must be 3. Now, just to sit there, it says include a check for your solution. So it'd probably be smart to go ahead and just take, and we're looking at the square root of 15 times 3 plus 4. 15 times 3 is indeed 45 plus 4. So I'm looking at the square root of 49, and fortunately I learned a long time ago that that was equal to 7. So this definitely checks, and my solution is x equals 3. Question 9 was kind of interesting. It says, consider this equation 2x minus 4y equals negative 10. First question is, what is the slope of this line? The way that I saw a lot of interesting techniques, and some of you got the right answers doing some really cool things. Uh, for me, what's most simplest is to consider the slope-intercept form of an equation, y equals mx plus b. And if I could transform the equation I'm given, if I could transform this equation into this form, right, then when I just look at the value of m, that would be the slope. So this is my technique, right? I'm going to rewrite this equation to get y alone, make sure it's in this form, right, mx plus b, and the value that's the coefficient of x, the number that x is being multiplied by, will be my slope. So if I do that, let's go ahead and write the equation here. We've got 2x minus 4y, and that equals the number negative 10. If I subtract 2x from both sides, I get negative 4y equals negative 2x, and then minus 10 still. And what I'm going to do now is I'm going to divide both terms, I'm sorry, both sides, all terms on both sides, by a negative 4. So I'm going to divide this by a negative 4, divide this by negative 4, and divide this by negative 4. Now, when I do that over on the left-hand side, very convenient, right? You can see there's this giant 1. So I'm left with just a y, and then that equals negative 2 divided by negative 4. That simplifies to 1/2 of x. And then negative 10 divided by negative 4 is positive 5/2, right, or 2.5. So what I cared about was getting this value right here that's the coefficient of x. And you can see the coefficient of x is 1/2. That means that the slope of this line has to equal 1/2. So that was the first part. By the way, guys, notice when I write the slope is 1/2, that doesn't include the x, right? X is not part of the slope. X is just, the slope is the coefficient of x. It's what x is being multiplied by. Now, the next question is, what is the slope of a line that is perpendicular to this line? And I like that we've seen visually what it looks like if I take a line segment and I rotate it through 90 degrees. I end up, if I have a slope triangle, my x's and y's flip in that slope triangle, and slope of that line becomes the opposite of what it was. So that's a nice way for me to visualize and think about what happens. If I want the slope of a line that's perpendicular to a line that has a slope of 1/2, I know that x and the change in y and the change in x have to switch places, so it's going to become 2 over 1. You can see they flipped, and it's going to have to become the opposite of what it was. So again, I'm looking at the slope of the line above, right? This line has a slope of 1/2. A line that would be perpendicular to that would have a slope of negative 2 over 1, or you could simply just write it as negative 2. So my answer here is the slope of any line perpendicular to the line in part A would equal negative 2. All right, given the graph at the right, complete the table of value. That should be plural, table of values, because there's not just one table of values, and find the equation of this line. So if we take a look at this, here's the graph a little bit larger, and you can see, for example, when x is the number -5, my y value is the number 2. I can read that from the graph, right? When x is -5, y is 2. Now the next thing up, it says, hey, what's x when y is 3? So if I look at when y is 3, right, I go up 1, 2, 3 on the y-axis and go back to x is actually -2. So that's why I see this dot at the point x is -2, y is 3. When y is the number 4, the x below is the number 1. And when x is 4, y is all the way up at 5. Now, I would say almost all of us identified those points correctly. Where we got into a little bit of trouble then is, okay, how do I now come up with the equation of the line? Well, a couple things can happen, right? One of the things is I could pick any two of these points that I wished, and I could calculate the slope of the line, right? The slope is the change in the y value divided by the change in the x value. And I could quickly do that because I know a whole bunch of x and y's, right? These are all x values, and over here I've got the corresponding y values. So if I wanted to, for example, find the change in x and y, I could choose to say, let's use, I don't know, I'll use this pair of numbers. Right. So that first point has I'm doing the y's first. So the first one has a y value of 3, and then I'm going to subtract 4 from that. So that's the change in y. I'll just say 3 minus 4. It's one way you can do it. And I get to keep the order the same for my change in x. My x is going from -2 to 1, so I'll just write -2, and then I have to write a minus 1. So you can see I've got the 3, the -4, and then for my change in x, I've got a -2 and a -1. By the way, because we're finding the change in x and y, this will always be subtraction here in the numerator. And then this will always be subtraction here in the denominator. So I've got change in my y value over change in my x values. If I simplify this, 3 minus 4 is -1. And then in my denominator, I've got -2 minus 1, which is -3. And this simplifies to 1/3, right? So the slope of this line is up 1 over 3. And you can see that play out in a bunch of the points here, right? If I go up 1 for y, I'm going to go over 3 values for x. If I go up 1 for y here, I'm going to, again, increase 3 values for x. So every single time every single time I have a rise of 1, I'm going to have a change in x of 3. So my slope is 1/3. Now that I know the slope, right, I need to find the y-intercept. And if you look, the y-intercept is kind of problematic. This is not a y-intercept. You know, it's somewhere in that region right there. If I look in the graph, somewhere in the purple circle. But I don't really want to identify where that's at there because it looks difficult to tell exactly what it is. So all that I need to do is select one of my points and use that to find the y-intercept. So for convenience, I'm going to go ahead and pick, I don't know, I'll pick this last point, the 4, 5. So in that, I have a y value and I have an x value, and I'm going to plug that into this equation, right? Y equals the slope times x, and then plus the y-intercept plus b. So if I'm using my point 4, 5, in that point, y is 5 and x is the number 4. So for y, I'm just going to place the 5, and then over here I'm going to have m, which is my slope of 1/3, and then I'm going to place x, which is the number 4, and then I'm going to add b. So it's not exactly pretty. I know that a lot of us get anxious when we see things like this, but we can handle fractions. So if I was dealing with this, 4 times 1/3 is 4/3 and then plus b. And what I would probably do now is subtract 4/3 from both sides. So 5 minus 4/3 is what b is. And then, you could consult with your calculator, and there's no problem with that. That's fine. But if I change 15, or I'm sorry, if I change 5 into thirds, that's 15, right? I can multiply the number 5 by a giant one in the form of 3 over 3. And I can transform this into 15/3, which is still the number 5, minus 4/3, right? And that is my y-intercept. And at that point, it's pretty nice to see, right? 15 minus 4 is 11. So 11/3 is my y-intercept, my value of b. That means that the equation of this line is y equals slope of 1/3 up 1 over 3 x plus a y-intercept of 11/3. By the way, if you think about that, 11/3, 11 goes into 3 times, that's 9, with 2 left over. So this number that's in the purple circle over here, that is the number, it's 3 and 2/3, right? Because it's up 1, 2, 3, and then up an additional 2/3. So 11/3 is 3 and 2/3. All right, the last question that I want to go over was from the back page, where it gave us three systems of equations, rather A, B, and C, and it asked us to pick a particular method pick each one of those as a candidate for solving by either elimination or equal values method or substitution. This particular one, almost all of you picked to solve using elimination. I'm sorry, using elimination. That's what I saw. And there's a couple ways you could go about it, right? Many of you chose to multiply the bottom equation by 4, and many of you chose to multiply the bottom equation by the number 3. In the first instance, I'm sorry, if you multiplied by -4, you could eliminate the x's. And in the second instance, if you multiplied both sides by 3, you would eliminate the y's. I didn't do it this way, so I want to do what I saw many of you do. I'm gonna take the second one. I'm gonna multiply this bottom equation by the number 3, right? So I'm gonna multiply the left-hand side and the right-hand side of that equation by 3. So for convenience, I'm just gonna go ahead and rewrite the first equation. It's 4x plus 9y, and that equals the number 11. And then below that, we have 3 times x, which is 3x. And then we have 9 times we have 3 times -3y, which is -9y, right? We've got the -3y, and we're going to multiply that by the 3, so we get -9y. And on the other side, I need 3 times 29. Well, I know 3 times 25 is the number 75, and I need 4 more, so I think I'm just going to add 12 to that. So 7 and 7 and 1 is 8. So I believe that's the number 87. So if this is 87 then, and I go ahead and combine these equations, right? I have equal things, and I'm adding equal things in different forms on both sides. So when I combine these equations, over on the right-hand side, when I add 87 to the 11, I get 98, I believe, right? 8 and 98, yeah. On the right-hand side, something that's equivalent to 87 is 3x minus 9, and I can add that, right, to the side above it. I can add it to the 4x plus 9. When I add that together, my 9y and -9y canceled. I'm left with just 7x. So x has to equal 98 divided by the number 7. And as I sit right here right now, I'm just like a little embarrassed because I'm not exactly sure what that is. And rather than show that I have actually any kind of fluidity with arithmetic, I'm going to cheat and use my calculator here. First time today. But 98 divided by 7 is the number 14. So I get that x is 14. Now, you were asked to write your answer as an ordered pair, and saying that hopefully jogged the fact that, hey, I need to find y also. So I don't know what y is, but I definitely know what x is, and I could use either equation, the top equation or the bottom equation, right? I'm going to go ahead and choose this second equation to solve for y. And to do that, I'm going to just use the new value of x that I just found. So I'm going to write 14, because that's what we found x to be, minus 3 times y equals the number 29. From each side here, we're going to subtract a 14. On the left-hand side, I get a negative 3y, and on the right-hand side, when I have 29 and we subtract 14, we do get the number, it's 15. That's great. 15. Now I'm going to divide both sides by a negative 3. Negative 3. It's real important that I catch that, right? Negative 3y divided by negative 3 is y. And over on the left-hand side, 15 divided by negative 3 is the number negative 5. So my solution is x is 14 and y is negative 5. And there it is written as an ordered pair. Using the elimination method, I eliminated y, and I accomplished that by multiplying both sides by 3. You can try this. It's great practice. Try multiplying both sides of the second equation by 4 and verifying that you get the same answer. Excellent practice. If you don't get the same answer, you made a mistake, the best thing that you can do is spend some time trying to hunt down where errors are. That's it for the review questions from the Chapter 6 individual test.